Okay, welcome back. We are going to go over problem 2 on our simple harmonic motion worksheet. This is on the back. Let me go ahead and read the problem. A small block is attached to an ideal spring and is moving in simple harmonic motion on a horizontal frictionless surface. The amplitude of the motion is 0.165 meters. The maximum speed of the block is 3.90 meters per second. What is the maximum magnitude of acceleration of the block? Okay, so let's think about how to start this problem. It's very helpful to start by drawing a picture. This is our most common example in oscillation problems and simple harmonic motion problems, which is some kind of a block, or you can think about the glider from the air track in lab, which is on a frictionless surface, so it can move back and forth, and it's attached to a spring, which is attached to the wall. So if you displace it, it's going to oscillate back and forth. And as always, with spring problems, we define the equilibrium point to be x equals 0, the location where the spring is neither stretched nor compressed. And we know that if we were to give this block some initial velocity or displace it some amount, it is going to undergo simple harmonic motion and oscillate back and forth between some maximum position, which we call the amplitude, and some minimum position, which is minus the amplitude. And so this block is going to oscillate back and forth. So that's our picture, and we always define the plus x direction to be when we are stretching the spring, and the minus x direction is therefore when we're compressing the spring. Okay, with that setup, which is the same setup for most of these spring oscillation problems, we have to then go ahead and write down our knowns. So they told us the amplitude is 0.165 meters. So it's going to be doing the 16.5 centimeter oscillation back and forth here. And we know the maximum velocity is 3.90 meters per second. Okay, those are the two knowns, and then let's write down the unknowns. The unknown they told us in the problem is the acceleration of the block at a specific moment, which is the maximum acceleration. So whenever that happens, that's what we want to know. We know the acceleration is going to be changing because the force of the spring changes based on your displacement. We want to know when is there the maximum acceleration and what is that maximum acceleration. So that's our principal unknown, but we can note there's a lot of other things we don't know. We don't know the spring constant. We don't know the mass. So there's a lot of other unknowns that we don't have. But this is our setup for the problem. So, okay, at this point, we can start thinking about what concepts would apply to solving this problem. Well, first, let's think about our unknown. Our unknown is the acceleration. So we know a few things about acceleration when it comes to an oscillating system or when it comes to a spring, right? We first know that acceleration is related to force. So let me write down that concept. I'll say this is the first concept we're going to use in solving this problem. And that concept is that acceleration is related to force. We have F equals ma. Right? So if I want to find the maximum acceleration, that happens when we have the maximum force. Okay, that's the first thing we can note. So as this object is oscillating back and forth between its maximum amplitude and its minimum amplitude, where does it have the maximum acceleration? As it's oscillating back and forth, it's where it has the maximum force. Okay, where does it have the maximum force? Well, this is a spring. That's the only horizontal force on the system, and we have a spring equation. We have the force of a spring, or the force of the elastic force, is equal to minus kx, where k is our spring constant, and x is our displacement. All right, so I can write this as the magnitude of our elastic force is just equal to the spring constant times the magnitude of our displacement. Right, just get rid of that minus sign for this purpose. And so the question is, when do we get the maximum force? Right? We want to find the maximum force. That is when our elastic force is as big as it possibly could be, which is when we're at our furthest displacement, when the spring is as stretched as it could be. And that's when we're out here at our max amplitude. So that's our first major concept, is that the max acceleration occurs at x equals a or minus a. It'll be the same magnitude acceleration in each of those locations, but in opposite directions. Right? So since the force of a spring increases with displacement, right? The more you stretch it, the bigger the force. The maximum force and the maximum acceleration are going to occur when we're at our max amplitude. So, okay, that's a key conceptual issue, is we just figured out when this acceleration occurs. The next concept we have to use is somehow to figure out the acceleration at that location. And we already have all the basis for this. We know that the net force is equal to mass times acceleration, and the net force is just the force of a spring. In the x direction, there's only one force. That's the force of a spring, and we know that force, so we can right away write down an equation for the acceleration that is going to be helpful to us in solving it. And so if I want to know the max acceleration, that's going to occur when our x equals our maximum amplitude. Right? Or perhaps it'd be better just to write this in terms of a magnitude, and therefore I don't have to deal with this minus sign at that location. So using F equals ma and plugging in our equation for the force of a spring, we can come up with a really nice equation, which is one we can use to solve for our ultimate answer. We want to know the max acceleration, and this equation will be useful for that. Okay, so looking at this equation, we already know that we know the amplitude. So we know this. That's going to be helpful when we plug it in. But we know that we don't know k or m. Those are both unknowns to us. And so although we have a nice equation which is going to be helpful to solve the problem, we can't solve it yet because we have two unknowns still. So now we have to think about some other methods, some other concepts that we can use to figure out k and m. And so now we have to start thinking, of all the different methods of solving these oscillation problems, which one could we now use? And we can get a big clue by looking at our other known. Our other known is related to velocity, right? They told us the max velocity, the fastest this cart is going to go as it oscillates back and forth. And so the connection we can make now is that velocity is very related to energy, right? Velocity and kinetic energy are very related concepts. And that's our link. That's our link that gives us the clue that we should maybe try to use energy concepts. Remember, we basically only have four methods to solving these type of problems. The first is that frequency and period are related to the properties of the object. The second is that force is related to acceleration, which we already used. The third is that there's an equation that relates position and time on our equation sheet. That's not going to be helpful here because we don't have any time information. And the fourth major concept is energy conservation. All right, we're on a frictionless surface. It says that in the problem. And so it's frictionless. There's no energy leaving the system due to friction. There's no external forces pushing on the system, which would be adding energy to the system. So all that adds up to the fact that energy is conserved in this system. And the fact that we have a known about our initial velocity, or not our initial velocity, but our max velocity, tells us something about the energy at one given location in this oscillation, which can help us solve for other unknowns. So k and m are unknowns. We're not going to be able to solve for both of them, but we don't need to know both of them. All we need to know is their ratio. And so let's go ahead and try to use energy to solve for their ratio. Right, so energy conservation tells me that E1 is equal to E2, right? It's basically saying that energy is constant. So I can pick one moment in time, and the total energy at that moment in time, time 1, is the same as at time 2. So I can set those times equal to each other and solve for an unknown. And we already know about the energy at one given moment, right? In general, the energy in a system which is oscillating is going to be a sum of its kinetic energy, 1/2 mv squared, and its elastic potential energy, 1/2 times the spring constant lowercase k times x, which is its displacement from equilibrium. Right? So that's a general equation for the energy, which is something which is oscillating back and forth. And so it's also the energy at time 2. Okay. Now we can look at this equation and we can pick two moments in time. We know that when we're at x equals 0, at this key location, something special happens. At that key location is where we have Vmax occurring, right? The maximum velocity happens as we pass through the equilibrium point. The velocity when we're out here at x equals a at the max amplitude is 0, right? At that point, it's turning around as this block oscillates back and forth. And then as it accelerates back towards equilibrium, it's experiencing a force which is accelerating it in this direction. But then once it gets to the equilibrium point, the force goes to 0, and then the force switches directions. So it's going to start slowing down after it passes through the equilibrium point. So the max velocity must occur at the equilibrium point. So I can pick this to be time 1. Because I know something key about that location. I know the position is 0, and I know the max velocity. So I know a lot about that time. And then I can pick this to be time 2. Because I know the position is a, I know that, and I know the velocity at that moment is 0. So I know a lot of key information about the energy at that location also. So I'll pick those 2 moments in time as my 2 times. And so if time 1 is as I'm passing through the equilibrium point, then the position is 0, because that's what the equilibrium point is, and the velocity is the max velocity at time 1. Okay, so that's my energy at time 1. Now I don't know the mass, but that's okay. That's what I want to solve for that. Looking at the right-hand side, at time 2, we have when we're at our max amplitude and our velocity goes to 0, we're turning around, so that's 0. And our elastic potential energy is 1/2 times the spring constant times our position squared. And our position, we know, it's our amplitude. So now I have an equation which has 2 knowns in it, right? I know my max velocity, I know my amplitude, and it has 2 unknowns. So I can't solve for either k or m individually because I have 2 unknowns, but I can solve for their ratio. And that's all I need here. So let's divide both sides of the equation by 1/2 so that the 1/2 just go away. And then, just giving myself a little more space here, I can solve for k over m. And that has to equal v squared, that's v max squared, divided by my amplitude squared. And I know both of those things. I can plug in and find that k over m has to equal 558.7, and the units end up being per second squared. And so now that I know that, I can go back up here to the equation we derived earlier, and now I know k over m. So now I can say A max is equal to k over m, which is 558.7 per second squared, times my amplitude, which I know, 0.165 meters. And so our max acceleration therefore becomes 99.2 meters per second squared. So this is a very typical oscillation problem in that we had to use multiple concepts to solve the problem. And that's the power of oscillation problems. We have this repeating motion, just given a few initial knowns, very few initial knowns, we can figure out a lot about the system. And we were able to do that here. So that's our answer. So thanks for your attention.